This is the quantum model of the atom, simulated in C++ using OpenGL. You've probably imagined atoms looking something like this. This is the model that basically everyone learns is what atoms look like. But what if I told you that this model is not only completely garbage, it's pretty much useless. Atoms don't look like this at all. And in this video, I'm going to take you from this very basic model all the way to the real physics that are the most accurate way to truly understand atoms. To start, we need a bit of a plan of action. You've probably learned of atoms being made of particles called protons, neutrons, and electrons. Protons are positively charged and electrons are negatively charged. The neutrons are the boring ones that are neutral, but they do have a mass which causes some interesting effects. But in quantum mechanics, these particles also behave like waves. And that's kind of an issue because that makes no sense. So to actually understand what we're doing here, let's start by wrongly ignoring the wave part and then working our way back up. We'll begin by creating a simple hydrogen atom with circular orbits. I'll create an engine struct that initializes OpenGL and runs a window in the main loop. A struct is like creating your own data type that can store variables and functions. I'll create another struct for our particles. Inside the struct, I'll store the position and charge variables. Now OpenGL renders everything in triangles. So to draw a circle, I'll create a function that iterates over the sine and cos values and multiplies each vertex by a fixed radius. Let's go with 10 pixels for the protons and neutrons and 2 pixels for the electrons for now. Then I'll add the position value of my particle to each vertex to make them follow my particle's position. Pretty neat. Now, based on the charge of the particle, we'll color code the electrons to blue, protons to red, and neutrons to gray. Then in main, we can create a list of particles. Let's initialize one proton in the middle and one electron to the side. And bravo, here we have an atom. The only thing missing now is for the electron to start doing donuts. We'll add an angle property to the particle struct only used for the electron, along with an arbitrary orbiting distance and an update function that adds to the angle each frame, along with updates to position. Then we can run this function in our loop. And there we go. Here is the hydrogen atom in its most basic form. Now, to create multiple atoms, we'll create an atom struct with a position and particle list. That way, we can create a list of atoms and nest the particle loop in another loop that iterates over each atom. I'll also add a circular outline for the electrons so that we can clearly see their orbit. Now, let's initialize two atoms side by side and see how that looks. Pretty neat. This is a traditional model of the atom that we've all seen at some point. But now, we need to take a bit of a step back because looking at this model, you'd probably ask, why is the electron orbiting the proton? Fundamentally, this is happening because of something called Coulomb's law, which is basically the gravity law in disguise that says that positive and negative things like to be together, like magnets. But here's the problem. Despite being almost identical to the gravity law, electrons can't orbit the nucleus like how planets orbit our sun. Our electron is constantly changing direction, and when electrons experience change, they radiate energy. So if you really think about it, why doesn't the electron just fall into the proton? I mean, when positive and negative magnets exist, they collide with each other, so what keeps an atom stable? Well, in 1913, Niels Bohr asked this question and came up with the Bohr model of the atom. It basically says that electrons can only exist around protons at very specific amounts of energy, called energy levels. If the electron moved any closer to the proton, it would have to radiate energy and leave that specific level, which would violate this rule. That's why it stays at that energy level and doesn't fall into the proton. Think of it like walking downstairs. If an electron tries to fall into the nucleus, it has to collapse to the lowest level. And once it hits the ground state, no matter how much it wants to radiate off energy, it can't physically go any lower because there is no lower energy level. So to make our simulation more accurate, we'll have to add these ideas of energy levels and radiation. I'll add an energy level parameter to the particle struct. Each energy level has a specific amount of energy. For hydrogen, it's given by this equation and measured in electron volts. Electron volts are basically joules, but like 10 quintillion times smaller. So for the sake of the simulation, I'll just convert energy directly into a radius to visualize it easier. Now our electron is currently in its ground state and can only rise energy levels if it receives energy from an outside photon. So let's create a wave struct. We'll set the position, direction, energy, wavelength, and frequency variables, and create a draw function that adds vertices in a wave pattern using the sine function. Because our electron can only exist at very specific energy levels, the electron needs a specific amount of energy to rise in energy level. If a photon has the wrong amount of energy, it will simply pass through. This is fundamentally why different materials only reflect back specific colors. We'll create a list of photons with the exact amount of energy needed to rise from energy level 1 or N1 to energy level 2 or N2. Iterating over the electrons, if a photon gets near an electron, we'll run an update function that deletes the wave and updates the energy, and thus the radius. Now let's initialize a line of atoms and a bunch of photons flying in from the right, and see how that looks. Okay, our electron seems to have increased its orbit radius, which shows that the photon absorption is working. But there's a bit of a problem. Electrons always want to go to the lowest energy level, which means that when an electron is excited, there's a time limit before they fall back down and release that energy back out as a photon. So let's add an excited timer variable into our particle struct. If an absorption occurs, we'll increase that timer by a small amount, and in the loop, we'll decrease that timer every frame by a small amount. Then in our update function, if the timer is 0 and we aren't at the ground state, we'll reduce our energy level and create a new photon in a random direction to release that energy. We'll color code the new photons to yellow and make it so that the electron can't reabsorb its own photon again. And that should be it. Now our atoms can absorb and release photons more than just once. We can also add some controls to spawn in new photons using the mouse and keyboard. Let's see how that looks. Isn't that neat? It's cool to think that this simple little action of absorbing and releasing photons is the whole reason we can even see colors in the first place. In fact, if we create a bunch of hydrogen atoms in a circle shape and shoot the light from a single direction, we get a mini entropy simulation. This is literally what happens to the Earth as it absorbs the sun's energy from one direction and emits it back in all directions. But now, we need to take a bit of a double step back, because there's a really big problem with this model. Before, I explained that the reason electrons don't fall into protons is because they can't leave their energy level. But this creates a bit of a paradox. If the energy level doesn't change, how can the electron accelerate around the proton? To summarize quickly, electrons have something called a magnetic field. When an electron is still or moving at a constant speed, things are fine because the field moves with it. But when an electron accelerates, it causes a distortion in the field which becomes a photon and depletes its energy. So an electron can't accelerate around a proton without releasing its energy. But it also can't release energy because it can't go down in energy level. So what actually happens is the electron kind of doesn't orbit at all. And this is where the idea of waves comes in. In 1801, Thomas Young was shooting electrons around at a wall through some slits and saw a constructive and destructive pattern, something only waves can do. But if you measure an electron's position, you can find it, something that waves can't do. So in reality, electrons are kind of a mix of both, a duality. Normal waves move through space, but an electron is bound by an atom, which makes it a standing wave, kind of like a string of a guitar. Let's visualize this real quick in our simulation. I'm going to edit the path of the electron to make a wave pattern using the sine function, and make that frequency of that wave relative to the energy. I'm also going to add a control variable to edit the electron's energy using my keyboard. And there we go. Now this isn't an actual accurate visual of the wave, but it represents how waves wrap around the proton, and there's something very interesting that we can observe from it. You'll notice that the wave doesn't always wrap around the proton completely. We have to tune our energy to specific values to get a perfect loop. And this is the very reason the energy levels from the Bohr model existed in the first place, because these specific values happen to be the values predicted by Bohr's model. At any point between these energy levels, the wave can't wrap completely around the proton. Thus, the electron can't exist in that state. So in essence, this entire problem of acceleration and energy levels kind of goes away, because this wave that wraps around the proton is the electron itself. It doesn't orbit or accelerate, and only specific amounts of energy can hold these waves intact. Thus, none of our laws are violated. And if you try to measure its exact position, the wave will collapse into a single random point, holding its particle properties. The idea of waves solves all of our problems. So basically, what we need to do now is ditch this orbiting model entirely, and draw these electrons out as actual waves. And for that, we're going to need to move our simple 2D simulation to 3D. In our code, we can start by creating a camera struct that will have a position and orbital navigation system, similar to Blender. Each of our particles will have a 3D position, and then in Engine, we'll take our 3D coordinates and project it onto a 2D screen using some basic maths. We'll also add a grid so that we can get a sense of direction and scale. To test this out, let's generate some random points in a box shape and see how that looks. Pretty neat. Here we have our 3D space ready. Step 1 complete. Now before, I drew the wave as a literal wave orbital, but that's not really how it works in real life. The electrons are in something called a superposition. Basically, until you specifically measure where the electron is, it essentially exists in all possible positions at once. And all these possible positions that exist at the same time form the wave pattern. So to visualize our wave, we essentially need to turn these random points into a probability map of where the electron could possibly be. We'll start by moving our particles to polar coordinates. Polar coordinates will be centered around the nucleus and use angles and distance to define the position. Then we can convert back to normal coordinates at the drawing phase. Now in our generation loop, we'll create the r, theta, and pi coordinates, then convert them back to normal x, y, and z using a function in the engine class. Let's test this out by creating 100,000 particles with random r, theta, and pi values. That looks pretty cool. Step 2 complete. Now we can move this coordinate sampling into their own functions called sample r, sample pi, and sample theta. These functions will give us the coordinates of our electrons based on how the wave looks. And to figure out how our wave looks, we'll need something called the absolutely goated Schrodinger equation. This is the Schrodinger equation. It connects the ideas of literal waves like sound waves to electrons. It's kinda awesome. For us, it contains something called a wave function that can directly give us the probability of finding an electron at any given point. Because rotating an atom doesn't affect it at all, by definition, the equation is symmetrical and thus uses polar coordinates, which we've already implemented in our code. Thanks to that, we can split this equation into its radial and angular components, and then solve them individually. Now, I'm not going to go too deep into the math because it goes very, very deep, but importantly, it uses something called quantum numbers, which are used to describe any electron's current state. N represents the energy level, which we already know about. L represents the orbital shape, as higher level orbitals have many solutions with many different shapes, and M represents the rotation of the shape, or which way it's facing. There's also S for spin, but that's not really important for us. These numbers directly affect how the electron wave looks. We already saw how N affects things, and the other two will become more apparent in our new simulation. Using the quantum numbers, for R, the radial equation becomes this big thing. We don't really need to know how it works, but solving down, we use something called the associated Laguerre equation, which is like for spherical binding finite 3D shapes what quadratics are for shooting arrow problems. And we come up with this. This gives us the strength of the electron wave at any given radius for any given orbital. Squaring this and multiplying it by r squared directly gives us the probability of finding an electron between any two radius points. For example, at the ground state, the probability of finding an electron between these two specific distances is about 11%. Pretty neat. We'll do a similar line of steps for the angle probability. The phi value actually ends up being a completely uniform distribution, aka it's completely random. So we only really need to solve for theta. The theta value uses something called the associated Legendre polynomials that does a similar geometric solution to the problem, and we end up with these two equations. Again, they give us the probability of finding an electron between any 2 points in radius or angle. Now we can take these probability calculations and plug them into our 3 sampling functions. To turn these probabilities into actual points, we'll use something called CDF sampling. We're basically creating a giant number line in the list, with higher probability sections being larger than the other. Then we can sample a random number and find where it lands on that list. That section will be the particle's coordinate. In main, we'll take our spherical coordinates and update our position with them before adding them to the particle's list. Our loop will iterate over this list and draw each particle like before. And that should be it. Let's see how this looks for the normal 2p orbital. Isn't that neat? We can now clearly see the shapes of the orbitals in all their glory. Even more cool is seeing how these 2D shapes relate to the actual wave of the electron. For example, in the 2s and 2p orbitals, you can clearly see exactly where the nodes are and where the regions of high probability lie. You can also see how the energy level affects the radius. For same orbits with higher n, it's almost like adding another layer to an onion. Pretty cool. Okay, before we start experimenting with the bigger orbital shapes, there's one more tiny thing that we're missing here. You see, a wave has something called a phase, and I mentioned before that the phi value is completely uniform, but that's because it actually stores information about the phase of the wave. Many people visualize phase with color, but we're going to visualize it with actual moving electrons. The moving electrons will represent the flow of the current of the probability. The probability current won't affect the actual density of the electrons at any given point, but in a situation where we have more than one atom, the phase does play a role in how they behave. So, the velocity of the electron is given by this equation. I'll create a compute probability flow function and a velocity component to the particles. Then in main, we can update the phi coordinate with the velocity. Also, I don't want to drag this video out too long, but I ended up being inspired by Minute Physics, who used a ray tracer to create each particle in a color map, so I also gave that a go. I'll spare you the details, but I created a ray tracer and made each particle a sphere ball shape with colors based on how dense they were in a given spot. And finally, here are the final results. It's honestly way more beautiful than I would have ever expected. I think the coolest part about this model is actually seeing the patterns between the orbitals and how the quantum numbers affect things. Real quickly, for anyone who may have got lost in the way, each of these dots represents a possible position of where an electron could be. Until you measure the electron and it collapses into any one of these dots, it essentially lives in all of these states at once, called a superposition. The flow of these electrons represents the current of the probability, which is also representing the phase of the wave. And each of the different shapes represents a different possible state of the electron, some with different energy levels or different orientations. If you want to learn to code in C++ like this, I recommend signing up for codecrafters.io, linked in the description. They recently became the #1 most starred repo on GitHub, so I really recommend giving it a go. I have a Discord, Twitter, and Insta if you guys want to contact me. The source code is in the description as well, and I'm currently working on a web version which will hopefully come out soon. For those who stuck around till the end, I just wanted to thank you all very, very much for 100,000 subscribers. This really is a dream come true, and I can't express how grateful I am for all you guys' support. I promise I'll try to upload more often, and till then, thank you very much for watching.